Here we have section 6.2, and we want to look at our definition of eigenvalues and eigenvectors and characteristic polynomial. Okay, so for our definition, we need to let A be a square complex valued. Now, so it could be real valued, but complex valued matrix. And X a complex, well, toss in non-zero here, a non-zero complex valued column vector with x equal lambda x, okay, for some lambda element of complex numbers. Not a very good complex sign there. Then if, anytime we have that, then we call X an eigenvector of A, and lambda an eigenvalue of A. Okay, so that's our definition. And then in order to find them, remember that what we're looking for is a singular matrix A minus lambda I. So then the polynomial determinant of A minus lambda I is called the characteristic polynomial. Okay. Well, of A, I guess. And the text says it's often denoted as CH sub A of lambda. Okay. And then the characteristic equation okay, so we had our polynomial, but then if we want our equation in order to try to find our lambdas, that's the determinant. So A minus lambda I is equal to 0. And so, what this says is the eigenvalues of A A, are the roots of the characteristic polynomial, polynomial of A. Okay, and so you know, if I'll just do real valued so the calculations don't get horrible. But if I just have a matrix like 1, 2, 3, 4, how about that? So if I have A equals that, then our characteristic polynomial of A is equal to, well, let's do A minus lambda I here. So that is just, all you have to do is put minus lambda down the diagonal with what you had. So we have that. Now when I do that determinant, I get 1 minus lambda times 4 minus lambda, and then minus 6. And so that is lambda squared minus 4 minus 5, minus 5 lambda plus 4 minus 6. So that's lambda squared minus 5 lambda plus, minus 2. Minus 2. Okay, so now our characteristic equation would be lambda squared minus 5 lambda minus 2 is equal to 0. And so in this case, we have our lambda equals 5 plus or minus the square root of 25 plus 8 all over 2. And so this is, it's not a, you know, a pretty sort of thing. 5 plus or minus the square root of 33 all over 2. So those are our two eigenvalues. So I could say lambda 1 is 5/2 minus the square root of 33 over 2, and then lambda 2 is equal to 5/2 plus the square root of 33 over 2. So I have that, and I can solve for my eigenvectors. It's not very pretty here with these. So what do we have? 1, 2, 3, 4. Yeah. So we have 1 minus 5/2 minus the square root of 33 over 2, and then 2, and then 3, and then 4 minus 5/2 minus the square root of 33 over 2. So I have that matrix times my x1, x2 is equal to 0. So if I simplify this, I get, well, 1 minus 2.5 is minus 3/2, so I get minus 3/2 plus the square root of 33 over 2, and 2, and 3, and then this is 8 minus 5/2 is 3/2, and plus, plus, right, plus the square root of 33 over 2. So I have that matrix times x1 and x2 equals 0. Now, hopefully, if I did this correctly and do my row reduction, I will get zeros in the bottom of this for RREF. So now I want to go through my row reduction process on the matrix, and so I'll have a minus 3/2 plus the square root of 33. I wrote a 32 up there. 33 over 2. 2. And now what I want to do is multiply through the bottom by the negative of what I have there, and multiply through the top by 3. That's how I'm going to do this, is multiply the top by 3 and the bottom by the negative of what I see here. And so when I do that and add those together, hopefully I'll get 0. So this is going to get a little ugly here. So let me, oops, kind of bring that down. So when I take 3 times the top thing, I'll get a negative 9 over 2 plus 3 times square root of 33 over 2. And the negative of the bottom times 3. Now, you know, this hopefully is obviously has to be 0, but I'll get 9, so plus 9/2 and minus 3 times square root of 33 over 2. So I knew that was going to be fine. Now the question is, do I get 0 here in this next spot? So I'll take 3 times the top, so I'll get a 6. And then I have plus the negative of this thing times that thing there. So I will have 3/2 plus the square root of 33 over 2 times 3/2 minus the square root of 33 over 2. Well, this is a good sign because, you know, so when I write this down, I get minus 3/2 plus the square root of 33 over 2. I get a 2. Now, this first part here in the lower left corner, obviously 0. Here, when I multiply that out, it's looking good because I have, I'll get this difference of squares, right? So I get 9/4 and minus 33 over 4. So that's what I got from that thing, and then I have my plus 6. And so minus 3/2 plus the square root of 33 over 2, 0, 2. So, you know, Sage would make this much, much quicker. But I have 33 and a 9 opposite signs, so I'll get a minus 24 over 4. That's negative 6 plus 6. I do indeed get my 0. And so there is not quite a row reduced echelon form because I haven't divided through by this thing. And now I just need a vector here, solution for this. So right at this point, what this says is negative 3/2 plus the square root of 33 over 2 times x1 plus 2x2 is equal to 0. That's the result of doing my row reduction. And so what I could do, you know, as I look at this, actually an easy answer for my vector is I could let x1, x2 be equal to, I'm going to take, all I have to do is swap the two coefficients and make one of them the negative. And so I'm going to go with a 2 here for x1 and then a 3/2 minus the square root of 33 over 2. And there is my eigenvector that goes with my eigenvalue. Okay, so my eigenvalue, eigenvector pair are that, guess I could call it lambda 1 was equal to, I got to come back here and find the darn thing, 5/2 minus the square root of 33 over 2. So 5/2 minus the square root of 33 over 2. And x1 as a vector, not x1 as a scalar, is the vector 2, 3 over 2 minus the square root of 33 over 2. Okay, and the eigenvalue is unique in the way I write it, but the eigenvector is not. So for instance, these are, the bottom here is divided by 2. I could just as easily have said, no, I want x1 to be 4 and the square root of 3 minus the square root of 33. In other words, just multiply it by 2. That's a perfectly good eigenvector. Or I could go with cosines and sines, that idea of a unit vector. And so I could write x1 is instead, so I should probably, sort of cross that out and then cross that out because it can't be equal to different things. But I could use, if I get the, oh, why did I put a square root of 3 on there? That should just be a 3. Okay. And so here I could use the unit vector 4 over the square root of 4 squared plus 3 minus the square root of 33 squared. And then 3 minus the square root of 33 all divided by the square root of 4 squared plus 3 minus the square root of 33 squared. Whew. Okay, so any of those eigenvectors will do. It's any vector that satisfies that equation, and we know there are an infinite number of such vectors. Right? Any multiple of that vector will solve that equation. And so I could use any one of these forms as my eigenvector. Okay. Now, in general, when we do this process, just to finish this off with the characteristic polynomial, is that, if you have A equal A, B, C, D, so this is just a 2 by 2 case, but actually it aspects of it do scale to bigger matrices, and you have whoops, I want A minus lambda I. So that's A, equals, gosh, A minus lambda, B, C, D minus lambda. That when we take that determinant of A minus lambda I, you get lambda squared, and then you get a minus 2 times a plus d. I don't know why I said 2 times. I needed a lambda times. I'm not, like I say, not very good with numbers. Okay, so I'll get minus d times lambda and a minus lambda times a. So I get minus lambda times a plus d, and then plus ad, and then minus bc. Well, if you look at this, what you see is that lambda squared is equal to minus the trace of a times lambda plus the determinant of a. And if you go to bigger n, okay, n greater than 2, and you do the same sort of thing, you'll get a lambda to the n, you'll get minus the trace of a times lambda n minus 1. Then you'll get a bunch of other terms in here, and then it will end with plus the determinant of a. And ooh, actually I need to think about that. I think it's always plus. That's a good question. I have to look at that, but so it does extend where that last term is, and I don't remember if it's it might be a -1 to the n, and sorry, right at the moment I don't remember, but that's not the real point. The point is that we will get a particular pattern when we go up in n. This stuff, not so sure what that is, right? But that first term of the lambda to the n minus 1 will be the minus the trace, and then we'll get the determinant as part of the last term. So kind of nifty that way. All right, so that is definitions of eigenvalues, eigenvectors, characteristic polynomial, characteristic equation.